Hi everyone, my name is Derek Chang, and today I'll explain the solution to the system of equations from video problem 3. We'll go through the parametric solution, understanding its geometric meaning, and compare it to the homogeneous system. I'll also touch on how matrices and row operations help us solve systems efficiently. To solve a system of equations like this, we often convert it to an augmented matrix. This makes it easier to organize and use systematic techniques like row operations. Each row of the matrix represents an equation, and each column corresponds to a variable. Our goal is to simplify the matrix into a reduced row echelon form so we can clearly see the relationships between variables. So as you can see here written at the top, I have written down the augmented matrix. I used row operations like row swapping, scaling, and adding multiples of rows to eliminate variables and isolate pivot positions. So a pivot is the first non-zero entry in a row, usually a 1, used to clear other values in that column. A column without a pivot represents a free variable. So after row reduction, our matrix becomes written here below. This simplified matrix shows us that x1 and x2 are leading variables, and x3 is free. We can assign it any value. Let x3 equals t, where t is any real number, then the system becomes, written below, x1 equals 1 minus t, x2 equals 1 plus 2t, and x3 equals t. We can write the solution in parametric vector form as written to the right of that. So, this solution describes a line in 3D space. It passes through the point 1, 1, 0, and moves in the direction of the vector -1, 2, 1. Each value of t gives a point on the line. When t equals 0, we get 1, 1, 0, and when t equals 1, we move to 0, 3, 1, and so on. This happens because one variable is free, so instead of a singular point, the system has infinitely many solutions. The free variables generate an entire line of solutions. So as drawn here, you can see the 3D line with the points 1, 1, 0, and arrow along to -1, 2, 1. So now we'll compare this to the homogeneous system, where the right-hand sides are all 0. So written below, I have the 3 equations where all of them are equal to 0, and row reducing this gives a similar matrix, but with zeros on the right-hand side. Solving this gives us the x homog is equal to t with the vectors -1, 2, and 1. And this solution describes a line through the origin in the same direction. So algebraically, both solution sets have the same direction vector, but the non-homogeneous system includes a specific point shifting the line away from the origin. Geometrically, this means the solution to the full system is a translated copy of the homogeneous solution line. In summary, the solution set is a line in R3, determined by a particular point and a direction vector. Matrices and row reduction help us uncover that structure. Comparing to the homogeneous case, we saw that the free variable create direction while constants shift the solution. Thank you very much for watching my video. I hope this explanation was very helpful. Have a great day.